13.3 here, we have a rod that's this long. It basically falls over without slipping, so it's like on a hinge, like a door or something when it's falling down. So the situation would look like this. There's the center of mass. Here's the 1.2, I'll call the length L, and it falls over, and so the center of mass goes from here to here. So it's really just an energy conservation problem. So it starts off here, it has an original energy, falls down. Where did all the energy go? It starts off as mgh, gravitational potential energy based on the center of mass, which is half L up, so h is half L, or L over 2. And when it falls, it gains, we're going to lose all that energy, all that mgh, and it's going to be rotational kinetic energy, so that's 1/2 I omega squared. Since it's a long, thin rod hinged right here and that doesn't slip, 1/2 I omega squared, the I value for that object is 1/3 ml squared, and then you're given all these numbers and you just solve for omega. One important point here, I missed this problem the first time I did it. I'd forgotten that 1/2 I omega squared actually is translational kinetic energy of every little bit of matter in this object. So if I took the 1/2 mv squared of this guy and this guy and this guy and all the little atoms in here, that is 1/2 I omega squared. So when it falls and it hits here, 1/2 I omega squared covers all the 1/2 mv squareds of all that. And so we call that rotational kinetic energy, even though it's the same as translational kinetic energy. This expression just yields all the 1/2 mv squareds of the rotating system.